the one that you don't want to use, because it's only give you a suboptimal solution, not the best one. So, well, today we are going to continue to discuss another items that allow you to calculate the hidden state better. Well, let's see what I have today. Okay, so far we have some detail in the material, which I will upload for you after the class today. Now, let's see what I have. Well, there is some example related to this one, which I will demonstrate how to calculate later, not on this slide, okay? I will show you in a sheet and hope you can understand what it means. And let's talk about another items. Well, this item is essential in hidden Markov model because it allow you to predict the optimal sequence of hidden state given the sequence of observation. And the problem of estimation now turn out to be the problem of estimate the sequence of state y that can maximize the probability of y given x. Well, you may wonder, why do we have this kind of formulation? Well, let's observe what we have here. Well, you are expected to get the probability of sequence of hidden state y given the sequence of observation x, right? And that's what we want. But we cannot get this probabilities right away because, for sure this is unavailable. So according to what we know about Bayes, you have probability of y given x equal to probability of x and y. This is John probability, right? Divide by probability of x, if you don't mind. And if it come to argument max, so you see that argument, well, let me clean this one, right? Okay, let me clean it. So you may have y star equal to argument max of over y of probability of y given x. This one is nothing but arguments max over y of p x y and divide by px. So px now become a constant in this formulation. So this is why you can ignore it, and it's nothing but argument max over y of p x and y. So this is the conclusion. You need the John probability of the second x and the observation x and hidden state y. All right, enough talking. How do we solve this one? Well, it's gonna be tough because in the end, what you end up is a John probability between the hidden state and the observation. What we do? Well, we have to write this in the original form. Let's see. You have this one is what we have with hidden Markov model, right? So you have, okay, y1, x1, x2, x3, y2, y3, yt, and sorry, this one, xt, yt plus 1, xt plus 1, and so on. So given the John probability, what you have, well, What I can derive here is the y from 1 to, sorry, I should not write this. Sorry, let's see. Y of 1 to t. Suppose that I'm estimating the sequence from 1 to t, okay, equal to argument max over y from 1 to t of John property p x from 1 to t and y from 1 to t also, right? And if you calculate this John probability, what you have is going to be equal to, oh well, I guess I will clean up this one a little bit, just a little bit. So let me write this. This is t, okay, yt minus 1 minus 1. Okay, it will be equal to the probability of this, which is arguments max of y from 1 to t of probability of xt given yt. Well, this is the emission probability, right? Multiply with this one. Well, this is nothing but probability of, this is the probability of, well, yt given yt minus 1. And, well, we have the rest here. Oh, this is nothing but the probability of x from 1 to t minus 1 and y from 1 to t minus 1. Wow, that's something we need. Looks good, but not so good according to what you see. We have a form of recursion, right? So in order to estimate this sequence, you need to maximize the John probability of x from 1 to t and y from 1 to t, and that can be broken down into those probabilities. So the thing is, can you take out yt? Well, it's not that easy. It's require a bit of computations. So it's gonna be arguments max over yt. You can take it out, but only with arguments max of y from 1 to t minus 1 over p xt given yt. Well, because the first term you are seeing here does not belong to the inside, so you can take that one out of the equations, okay? And again, you can multiply with p of, sorry, yt given yt minus 1. So looks like this transition property stick them together and you cannot separate them. There's no way you can do that. So just stick with that, and property of x from 1 to t minus 1 and y 1 to t minus 1. Well, this is odd. This is a lot of issues you may encounter, and given the formula, you cannot understand how to solve it. Actually, if you keep expanding, I don't think you can find a good way to express the algorithm. So I will show you how to solve this one using the dynamic programming scheme. What we have here is we are trying to do it in the way that is the best ever. Um, how can I say this is? Look at the formula. It's hard for you to tell how the RM works, so you have to see it through some example. So let me discuss a little bit before we jump into that part. Okay. So this algorithm is designed by V2B. He's a mathematician, and he make this algorithm available for you. And the basic principle of the algorithm is using dynamic programming. And so this is what you end up, like as mentioned earlier. You cannot separate yt and yt minus 1. Therefore, all of them stick together in a sequence of formula. But it's not too bad because given this, you can still solve the problems. And let's see what we have. Okay. Thing about it, what you observe is that this whole term can be maximized by the sequence from yt to t minus 2, which not related to yt and yt minus 1. So you can take that one out of the equations, but that's not so helpful. And I will show you a way to calculate it. And so here they give you the dynamic programming algorithms to solve the problems. So first, you know that you can compute the probability, the joint probability of the first state and observation p x and x1 y1, right? It's easy for you to find y1 that can maximize this sequence for sure. But then you have to go forward to see what you can do, which means you are trying to find the sequence from y1 to t minus 1 that maximize this probability, this joint probability. So overall, you need to form the joint probability of the sequence. And then, given that, you can select the YT that can maximize the whole sequence. Well, this is hard to explain to you how it works. So I guess I will jump into the calculation part, which is easier. So this is some detailed step which are not so helpful for your understanding. So I guess I'm going to jump to that part. Okay, so let me stop the slide here a little bit just for a moment. Um, Let me jump to this part. There we go. So you are seeing the sheet that I'm preparing. Nothing here, of course. So I'm going to fill in a bit of information. First, according to the example that we discussed last time, we have the transition probability as well as the emission probability. So I'm going to make it into a table. So I got transition, okay, and I will have let's see, uh, should I have it y t minus 1 to this is y t. Oh, sorry, this is y t and z. So from yt minus 1 to yt, what we have. So let me have party. Let me have pop. Let me have TV. Let me have study. Those are for hidden state that I can get. And YT here will be again party, pop, TV, and also study. So I will give you the transition probability from party to party, which is 0.05, right? And from party to pop, you will have, let me see, party to pop also 0.05. TV will be 0.7 and 0.2. Now, if you calculate the sum over this sequence, it should be 1, right? So that means we are doing thing correctly. Now, I think I would change the column sign a little bit here. Resign. How about 50? Okay, that's good. Good for me. By the way, let's do it with the pop. So you have from pop to pop. No, pop to party is 0.1. Pop to pop is 0.05. Pop to TV is 0.6. Up to study is 0.25. So, okay, I guess I will figure out this. Okay, thank you. Oops. Okay, just to verify if I made any mistake. So from TV to party, I will have, okay, 0.1. From TV to pop will be 0.3. From TV to TV is 0.4, 40%. And last, we have 0.2. Looks good. So from study to party, I will have 0.25. And from study to pub, we will get 40%. From pub study to TV, I'm sorry, will be zero point 0.3. And last but not least, we have this. Okay, everything is correct. So I have transition probability. Now, you may need another table called emission probability. So I will have, again, something similar to what you have seen so far. What I have is, well, yt, here's xt, xt. Okay, so for yt, looks like I'm going to copy this. For xt, I will have something like tired, hungover, okay, scare, and finally fun. So for state overall. Now for body, I will have 0.3, 0.4, 0.2, 0.1, which I already have. And for pop, I will get 0.4, 0.2, 0.1, 0.3. Okay, for TV, I will have 0.2, 0.1, 0.2, 0.5, which I believe is correct. Study will be 0.3, 0.05, 0.3, 0.35. So just verify thing, I will have the sum over all of it. So here we go. Okay, they are correct. Good. So I would like to make them. Okay, so you have thing ready in your hand. Now it's time for us to do some short up modification. Now, first, I'm going to show you how to do the forward items. Okay, forward items. What we have is a sequence of 8YT. So I may copy this one. Let me show it here. All right. So for XT, now you will have a sequence of state. Let me see what is the observation we have. Tired, tired. Oh, may I write this way? X1 equal tired, X2 equal tired, X3 equal scared. Okay, now if you remember what we have discussed so far about the forward items, we need to calculate the number alpha, right? So what is alpha? Alpha is the joint probability between yt and xt. So alpha one of y1 is equal to the joint probability of y1 with x1, which I believe you guys can get it. It will be equal to the probability of observing tired given the state party multiplied with the probability of well, you know, you need the prior, the probability of party, but because you have no information about that, just assuming they are equal 0.05. Okay, so there we go. You can have the first state. Now, if I do this, okay, whatever, that's fine. So if I do this, you can see that this one is the maximum, right? So I can easily conclude y1 equal to pop, right? Yes, the principle of forwarding is to calculate the state right away. So how about a2 of y2? Well, for a2 of y2, if you calculate according to the formula, what we have so far, do you remember the formula, or do you need me to explain about it? Um, well, if you recall the thing, it will equal to, well, the probability of observing tired, which is y2, given the state, multiply with, well, something we have to do. Well, it's the probability of yt given yt minus 1 multiply with the previous alpha. So this is the previous alpha multiply with the transition from party to party here, plus this 1 multiply with the transition from pop to party, which is this, right? Plus this one multiply with this one, plus this one multiply with this one. Okay, there we go. So you have one value. Okay, let me have another one. So this is the observation of observed tired given you are in the pub and multiply with, well, this one multiply with the transition from party to pub, which is the second column you are seeing here, right? Let's we do it a little bit quicker than normal. Let's, let's C7. Okay, there we go. I should have the observation here. Oh, here, right? Multiply with here. You transition from party to TV, okay? Plus multiply with D5 plus N6 multiply with D6, right? Plus and 7 multiply with D7, right? Looks good. Our next one equal to you have H7 multiply with, well, and what? And 4 multiply with not D but E4 plus and 5 multiply with E5 plus and 6 multiply with E6 plus and 7 multiply with E7. Okay, so we have everything ready according to what we know. Oh, sorry. I think I made a mistake. So again, this one will be okay. Delete this one. Add another rules using color scale. Okay, I'm done with this one. This one, let me add another rules using color scale. I'm done with this. And this one, let me add another rules using color scale. I'm done. Okay. So here we go. In this case, I can easily give you y2 equal TV. Okay. For this one, let me have A3. Now this one, you know how to calculate. You observe scale. So the first thing you have is J, right? Multiply what? This one, O4. O4. Multiply with the transition from party to party, which is this, right? Plus, so we have O4 B4. So you have O5 multiply with B5 plus O6 multiply with B6 plus O7 multiply with B7. Okay, you have one number. Let me have another number. This number will equal to J what? So you would have J5 multiply with, let's see, you will have okay, if I recall correctly, so O4 multiply with top, right? Okay, transition from party to pop, so you have C, okay, C4 plus O5 multiply with C5 plus O6 multiply with C6 plus O7 multiply with C7. That would be another number. So let me have another number. One will be J6. If I recall, yep, J6 multiply with, you have uh, O4 multiply with B4 plus O5 multiply with B5 plus O6 multiply with D6 plus O7 multiply with D7. Oops, what's the problems? Okay, sorry, what's that? All right, let me continue it with J7 multiply with, you have O4 always with O4 multiply with, you have okay, E4 plus O5 multiply with E5 plus O6 multiply with E6 plus, sorry, 6 with O7 multiply with E7. Okay, so you have everything ready, and there we go. It's easy for you to give y3 equal to TV. So the first day, he go to the pub. The second day, he watching TV. The third day, he watching TV. So looks like it's explained why he looked tired. for 2 days and then scared because he didn't study anything. Wow, that's the reason behind the scenes why we need four items. But again, this is something that you cannot trust because it's a greedy items. Right, this estimation is not 100% correct. So you may want to do some sort of items like let me say B2B, B2B items. And we will do something very similar, but this time I'm going to save some space. Let me show you. Okay. Okay, let's work with B2B because this is what we are interested in, right? So, what do you have in mind? First, we need to calculate the John probability, but before that, let me have here x1 equal to tired, tired, and scared. Okay, those are some state unit. Now, first, for party, the very first John probability you have is what? The very first John probability you have here in if yt is party and xt is tired, that John probability will be equal to the observation tired when you, yeah, here multiplying with the prior, right? The prior is no, the prior is 0.25. So you get that number. The first column is the same with forward items because that's initial point, right? So I have h5 multiplied with 25. You have h6 multiplied with 0.25. You have x7. Now, will you make the conclusion here? Well, I don't think so. We don't make the conclusion yet. But then we have to calculate the John probability of the sequence of hidden state given the sequence of observation. So, according to what you know in the VTB for algorithms and the formula that I just write for you in the slide, you need to go from this state to the next state is party, but observe tired. Okay, and there is another chance that you go from pop, that you go to pop, from pop to party. Okay, so you have totally four cases. You can go from party to party, you can go from pop to party, you can go from TV to party, and so on. So the John probability now will be equal to this one multiplied with the transition from party to party, which is B4. Okay, this is one number. And you have to multiply them with the the observation. But I think I don't need to multiply it yet because it is separate from what you know so far. So I can skip that one. Let me have here multiply with the transition from pop to party, which is B5, right? If I recall it correctly, B5 here, okay, from pop to party. And given that, given what you see so far, I can easily view this by equal to C21st multiplying with the transition which is B6, and here we have C25 C25 multiplying with uh, the transition B7. Okay, that's it. So you have four probability, the John property from x1 y1 multiplying with the transition from y1 to y2 multiplying with the emission property, the px2 given y2, right? And so if you multiply with this one, so this one will equal to the emission probability, the chance of observing tired when you stay in the state pi, y2 is pi, okay? Multiply with the maximum over this four number, okay? So we have this one. It sounds a little bit odd. No, it's normal, absolutely. So I can show you this one. Conditional formatting. Let me have color scale and let me done with this one. Okay, easily I can get this maximum John probability come from this one. Okay, which means it's come from study and then you go here. This is the maximum. Now I can repeat that process. It will be equal to C. C what? Um, that is C13 multiply with the transition from party to pop, which is the second column we have, C4. Okay, 1 equal to what? C17 multiply with C5, right? Okay, this equal to C21st multiply with what? With let's say C6, and finally you have C25 multiplied with C7. Okay, so those four numbers, which one is the maximum? This one. Okay, and so you have what the probability of observing tired given you in pop, which is H5 multiplied with max over those four, and you know what it is, right? Okay, so I will do this again. This one will be C13 multiply with D4, okay, equal to C 13 plus 4, 17, okay, multiply with D5 equal to C21 multiply with D6 is equal to C25 multiply with D what? 7. Just kidding. I just try to have fun with this one. Okay, that's it. And you see, I have to calculate a lot. That's not something I prefer, but if I have to, I have no other option, you know. So I have again C13 multiply with uh, oh, the next column is E, right? E4. So I have C17 multiply with E5 equal to C21 multiply with E6 equal to C25 multiply with E7. Okay, that's way too many calculations, but that's fine. I'm not going to complain about it because I know what I'm doing. So I need the emission probability here. It's gonna be tired given u in TV, which is h6, right? Multiply with max over this four number. That's what I have. I can also give you this h7, okay, which is the emission probability multiply with the max over this four value. Okay, so at this moment, at this step, you have four John probability according to four possible option for y2. And you know, if you can specify the maximum, that's good for you, right? But not yet. We can wait because at the moment you have one more observation to process. So you don't have to make decision right now. What you do is keep going forward in the way I do before. So I'm going to have E17, E13 multiply with B4. Okay, that's transition, and you keep repeat the process. So you have E17 multiply with B5 is equal to E21 multiply with B6 is equal to E25 multiply with B7. I keep doing this job. Sorry, I will try to make it quick for you. So E13 multiply with C. Let me move to C. Okay, C4. E17 multiply with C5. E21 multiply with C6. This one is E25 multiply with C7. Okay, and this time we have D. So E13 multiply with D4. Okay, this is E17 multiply with D5. This is E21 multiply with D what? I mess up. Sorry, just my head is explored. We have E25 multiply with E7, and last column, I guess, too much for me. Multiply with what? E, right? E4. Okay, finally, I have E17 multiply with E5. This is E21 multiply with E6. And finally, you have E25 multiply with E7. So that's it. That's what I need. Now I'm going to add the color scale like this one. I need to add the scale for this one also. Oh, sorry. Then let me add another rules. Color scale. Then this is what I need. Rules scale. Then. All right. So I can make decision right now. Let me have this one is the chance of observing scale given you in party here J4, right? Multiply with the max over those four number. Okay, so there we go. We have one value, and for sure you can have this one equal to I missed that. Let's see. This is J4, right? So here I have J5 multiplied with max over this 4 number, the emission multiply with that one. And so you have this is J5. So this one will be J6 multiply with max over those 4. Okay. And finally you have J7 multiply with max over this 4. All right. So let me tell you, in the end, you have the Jones probability of those 4 number. What you need to do is choosing them and find the maximum one. Okay, so it looks like the maximum one is here. Now you can conclude that y3 equal to what? TV. Okay, make sense? Did I make something wrong here? Just tell me. The thing you may want to note is that if you stop at the second state, you will see that there is two John probability that give you the same number, which means you cannot make a good decision here because either of them can lead to the optimal state. So that's the problems. We don't want that. So we do backtracking from here. You end up with this one be the maximum value, right? So it's according to the state over here. So in order to obtain that maximum, you come from here, which related to the transition from pop to TV, right? Which give you here. Okay, so this gives you y2 equal pop. And then from this one, you know, in order to achieve this maximum, this value, in order to achieve this maximum, you must come from this one, which is here, from study. Okay, so you can get y1 equal to study. This is what we have with V to B. So in the end, we can conclude that the first day he studied, but the second day he go to the pub, and then the last day he go to watch TV. That is why he have some observation like that. Of course, if you study, you feel tired, and you go to pub, you also tired. Instead of study, I don't know, but yeah, this is what we have with B2B. You guys can check it out at home. Of course, you are at home right now, so you can check this result and ask something if you wonder about this calculation. But again, it's involved two phase, forward phase to calculate values, but you have to remember where is the maximum value, and then you can go all the way using backtracking. And one thing good about this number is that if you use beta b, the process involve only and only the multiplication operation. So there is a problem with mm, zero multiplication. I mean, uh, in the process of calculating, maybe you encounter a phenomenon like the number is too small and it's not good for your calculation. So in that case, instead of multiplying thing, you can you can sum them up. You can add the log instead of multiplying. Okay, so it gives the same result, but the number is easier to read. For example, let me show you. I can modify this one by having this be the log of this one. It doesn't matter what log you want to perform. That's fine to me. And instead of multiplying, you can just sum them up. Okay, so you may have some big number like this one. Okay, it's not a big number. It's just some number, but obviously easier to read instead of those number. So I can do that. Normally this log function give you what the log of 10, if I remember correctly, or the logarithm. I don't remember. But it doesn't matter to me. So you may have this log plus the log of this one, okay, and you may have the log of this one plus the log of this one. Okay, and given that the number doesn't change much according to this one, you can have this is also the first one is log, right? So you can just plus log of p4, add them up instead of multiplying. Then you will have some nicer number, even though it's not so easy to read. Anyway, okay, this one gives you plus log of p7. Okay, do I have the right one? Okay, one c13 plus log of c14. Let me show you, they end up with the same result. So okay, but I have the first number here. What about this one? Um, yeah, you get the log of this one plus maximum. Okay, so okay, I'm about to finish, so don't worry. It will be quick. So this one plus log of b4. Okay. This one gives you plus log of b5. This one gives you plus log of b6. This one gives you plus b7. This one gives you plus log of c4. Hmm. I'm about to finish. Was kind of hard work, I believe, but I have no other choice. So ah, that's too much for me. I don't like it, but this is what we have to do. And configure. Mhm. Okay, so overall, what you say is that if I change from the normal probability to the log functions, the calculation looks easier to read because now the number cannot decrease to zero, and we can easily capture the idea. And also, we only have add instead of multiply. That's a good thing. And what you see is that we end up with the same result. TV pop, right? And this one gives you study, study pop TV. All right. So this is how you do B2B. And B2B is a very nice algorithms. In fact, it gives you a way to calculate the hidden state, the optimal hidden state given the sequence of observation. All right. So keep that in mind. You can use this one for your work, and it's very handy. Okay. So that's it. That's about hidden markup, and I hope that you can learn something from us. All right. Then I guess I will come back with the material a little bit before we finish this part. So we have to talk about how do we measure the probability. So let me have. Oh, looks like I lost connections. Anyway, that's fine. I don't mind. Join it. Okay. Uh, okay. Share screen. Okay. So this is what you have to do. You backtrack from the ending point to maximum probability, and then you you can get the optimal state. But the questions we care about is how do we measure how do we train the model actually. The training process is like estimating the probability, because what you have is the topology of the network, right? You know the relationship between those data. So given that, what you're interested in is how do we calculate the emission probability and transition probability? Well, there are two ways to do that, either supervised or unsupervised, your choice. So let's talk about it. In supervised scheme, you have the data and you have the label on your data. Then you can use, well, let me say, you can use the statistic to measure those probability very easily. There's no doubt about it. So in order to calculate the prior, the probability of seeing yi, the hidden state, will be the number of seconds start with yi. So remember, you always care about the very first hidden state of the sequence. So the prior now will be the number of sequence start with that hidden state divided by the total number of seconds, right? That's very simple. And then for the transition probability, you can count how many sequence transition from yi to yj, right? And divide by all the sequence transition from yi, all right? And for the emission probability, you can count the number of pair, between x and y, and then divide by all the hidden state yi. Now let me count this one. So first, let's look at this example. In the supervised scheme, you have the data, right? So now let's counting thing. So in term of prior, we have to take the prior, right? So I would like to calculate the probability of y equal f. Well, this one is equal to, let's see, 1, 2, 3, 4. Okay, so luckily in this case it's equal to 4 over 8 seconds. So you get 0.5. And you know what happens after that, so I don't mind. So you have prior, right? And then you are interested in compute the, let's say, the transition probability. So may I calculate the transition from F to B? If I calculate the transition from F to B, I have probability of y t equal to B given y t minus 1 equal to F. This is a transition probability from F to B, right? It's equal to FB. How many seconds I have? FB. FB. F, no. FB. Oh, we don't have FB here. FB. 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 Okay, so you have about 6 over how many how many uh, how many pair from coming from F? Can you count? FF 1, 2, 3, right? And 4. You have 5, 6, okay, 7, 8, 9, and 10, 11, 12, 13, 14, and 15, and 16, 17, 18, 19, 20, 21st, and 22, 23, 24, 25, 26, 27, 29. So it's going to be 6 over 29. This is gonna be some number like that. Okay, 6 over 29. And you can keep counting. You can get the number you want. Okay, that's how it works in supervised scheme. Now for emission probability, for example, I am interested in this number. So it's going to be the probability of x equal h given y equal to f. This one equal to, let me count fh, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, 13, and 14, 16, oh no, 15, sorry, 15 and 16, 17. So you get 17 over all observation you can have from the state F. So it's gonna be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21st, 22nd, 23, 24, 25, 26, 27, 13, 4, 31, 32, 33, 34, 5, 6, 7, 8, something like that. All right, so you have that emission probability, and it's all come down to how do you count number of pair. So this is just the hard work you have to do. But given all the data, you can calculate the emission probability and transition probability. Um, but that's so not realistic. I mean, in the real application, it's hard for you to labeling all of your data. Sometimes it's very tough. So we may need to propose some idea to train this model using unsupervised scheme, right? And in order to do that, what you are saying is we have to make some initialization first. If you have no idea about the hidden state, the label here, assuming that you don't have the label, you only have the data. But what you know is the topography. You know that you can transition from state to state like this one. Then at the beginning, let's assume that I will have the equal probability. For example, the prior is 0.5, 0.5, and the transition from F to F and F to B are the same. So you have 0.5 here, 0.5 here, and other direction also have 0.5. And the emission also 0.5, 0.5, 0.5, and 0.5. Okay, so this is like it's gonna be the initial probability you have, and then you can apply B2B in this hidden Markov models to predict the hidden state. And as you have the hidden state, what you have to perform here is recalculate the emission probability as well as transition probability to get the new model again. And as you have the new model, you are going to use B2B one more time to get the label or hidden state. And that process keep repeating until it converts. I mean, the probability no longer change. Okay, and we are done. That's how you train unsupervised. Well, that cost you a lot of operation in training, but the Markov compared to some other models in machine learning is still very small and it's easy to learn. So I guess you guys can use that and train it very quickly, given that you have data. Remember, you need a lot of data in order to make this estimation correctly. Okay, so these are some notes that I have in the material. You guys can check out later. Okay, and the full process of hidden Markov is there. So what we are interested in is you can apply hidden Markov model for various problem in machine learning. For example, you may interested in using hidden markup model for a problem called NER, name entity recognition. In some other document, some other paper, they will this one POS, sorry, POS is a abbreviation for part of speed. Okay, so it's like you are trying to predict and gather the label for your text. Look at this. You have a sentence called Facebook CEO Zuckerberg visited Vietnam. And so you are interested in a few names here, like Facebook, like CEO, like Zuckerberg, like Vietnam. So what we have is, well, Facebook is like the organizations, okay? And CEO is something that you may not wonder, you don't care. But Zuckerberg is the name of a person. So you say this is a person. And visited is something you don't care. So you may skip it. And Vietnam is a location. It depends on your definition, okay? So depend on what problems you are having, you can define those hidden state differently. So look at this. The input is a sequence of observation, and the observation you have is it can be a token, or may you input is an embedded vector of that word, of that token, your choice. Whatever the case, you have the observation, and the output is going to be, no, not the output, sorry, the hidden state is going to be some label that you assign on those word. And so as you can see, can be modeling this can be modeled using hidden markup model. Anyway, using this as one way to solve the problems, but in some other case, you know that you can divide the sentence into something more complicated. The full transition, yeah, this is the topography of the hidden markup network, can be represented like this one. So this at the beginning, you can observe the person, you can observe the organization, you can observe something else. So this is the prior. Those probability are the prior of the first word you can see. So maybe according to the statistic, in most of case, the very first word you observe is the name of a person. It depends on your data set. I don't know, but you do the statistic and you can get that prior. And then when you observe a person, you can observe the next word also another person. No, the same person maybe. So it looks like you have the name, and the name in any language can contain one word or maybe more than one, right? So you have this transition. And also from person to organizations, there are two directional relationships. Therefore, you may have some some statistic over here given the data. All right, and yeah, I think that's all you need for NER. And this is not new. It has been invented in 197 no yeah 1997, I think. It was very old, and people still think it's very useful. But nowadays, with the trend of deep network, people no longer use hidden markup model for this one. But by no means I'm saying that this is unuseful, because in some particular application it can also be good. And if you don't know, just in the hidden Markov model has been applied in speech recognitions for a long time. Before some deep model appear, hidden Markov model has been used for speech recognition, and it did a good job in that. However, the accuracy is still very limited, but at the time, and with some small application, it's still good. And the good thing about hidden Markov model for that application is it require uh, not much in the hardware, and so you can apply it very nicely, run fast, and people apply it in some application at the airport and some other place. Who knows? So you can try. Okay. And well, this is some other note. Maybe a person, some label we have several part. So like beginning, the intermediate, and the ending. So if that is the case, then you may have more hidden state in the setting, but that's not a problem. Okay, so that's it. That's all about the hidden Markov models. And if you are interested in this one, you can read some other material. Of course, I'm not asking you to read the paper, but just for the sake of understanding, you guys can uh, follow some paper. Maybe you read some new paper. This one very old. I don't really like it, but for the history of this course, we keep this slide just for reference. Okay, you don't have to worry about it. All right. So that's about hidden makeup models. Do you have any questions about it? Do you have any questions or anything you want to discuss? Just tell me. Looks like this one is easy, right? Um, I can realize that a lot of you may not care much about the hidden markup models because you don't find it to be very useful. But trust me, in some application nowadays, still hidden markup model is very handy. It's not that people don't want to use it, but because for a lot of researcher, including you and I, we care about accuracy, and also we engage a lot in well we engage a lot in new technologies like deep learning. So we are not so interested in the classic one. That's fine. If you know it, someday you can apply it. Not necessary to be right now. Okay, so I guess you don't have any trouble with hidden Markov models. Let me move on with another topics. So which part of B2B items that caused you trouble? Just tell me which part, the calculation process or something.
I think the calculation process.
Okay, so according to what we know, let me show you the slide again. No, not slide. I guess I will show the sheet. Ah, yeah, this one. Just make sure that you understand what we have in this calculation sheet. All right.
Uh,
So
I teacher, about the system, I understand the process, the step you calculate, but
mhm.
in the math, I don't understand quite truthfully, deeply about the math behind the algorithm.
Okay, the math
Yes,
behind the items is all
it's
right.
in the slide 21 or slide 22.
Mm-hmm.
Yeah.
Okay, okay. Slide 21 to slide 22. Let me see. 21. That's it. Okay, I got it. So wait a minute. I will show you the slide. Okay, so as you are looking at the material, what you see is that for V2B items, we tend to find the sequence from Y1 to T, right? That maximize the Jones probability of the observation and the hidden state. This is normal. And when I extend that Jones probability, we got it, well, the transition probability yt to t minus 1 to yt multiply with the emission probability and multiply with the rest. Is that okay?
Mm,
We are okay at this point, right? Here,
so, uh,
look.
so, from the step one to the step two, I don't know. Is the difference when you check the YT and uh, max from Y1 to T equal to max YT and max Y1 to T minus 1.
Also, okay,
Yes.
okay. Let's take a look. This one is no, this one is xt minus 1, right? This one is xt. This one is yt. This one is yt minus 1, and so on, right? This is x1, this is y1, y2, x2, and x3, y3. So if you calculate the John probability of the whole network, then it will equal to, according to the theory of hidden Markov that we mentioned earlier, the assumption, then that John probability equal to the probability of observing xt given yt multiplied with the probability of transition from yt minus 1 to yt and multiply with the John probability of the whole thing here, right? So the probability of the whole thing you see is the one I highlight right here, this one,
Yes. Okay, teacher.
right? This is what I'm highlight the whole thing. That's the recursion. So what you have is now when you extend the formula, you got this two part, and the form of it is like a recursion. So suppose that you can find the joint probability of x from 1 to t minus 1 and y from t from 1 to t minus 1. Then you can transition from yt minus 1 to yt. Okay, so how many positions, oh sorry, how many value of t minus 1 can you have depending on the problem? So for this problems, for this setting, you have four state of yt minus 1, right?
Yes, yes,
So you have four chains to go from t minus 1 equal to pi to yt, and yt has four chains also. And that is why in the sheet you have to calculate for probability. Is that
mm,
okay?
yes. Okay. Uh,
So there is four chains from going from y. Okay, look at the sheet I just show you. If previous state yt minus 1 is parity, then the yt has four state: party, TV, pop, or study, right? So if you are calculating the joint probability where yt equal to party, then how many probability you can get when you calculate yt minus 1? 4, right? There is
yes.
four state of yt minus 1 to go from there to yt. And that is why in this formula, you break down, you take out yt minus 1 out and yt out also.
Oh, okay.
Mm, yeah, I guess explaining in Vietnamese is easier, but yeah, I hope that you can get the idea. So previously, yt has four possible states, and then now when it comes to yt, you also have four possible states. So if you want to maximize the sequence from yt minus 1 to yt, there is totally 16 combination, right? 16
Yes,
combination. Yeah,
yes,
that is why you see in my calculation, I have four, um, first I calculate four possible transition from yt minus 1 here. I calculate this one first,
yes,
for possible transition from t minus 1 to yt. And then there is for yt. That is why I have 16 value. Okay.
yes.
And so I choose the maximum among four possible combination of yt minus 1 to yt. All right.
All
And
right.
then I pick the probability that maximize over yt. So the max over that four value. So if you observe the sheet I shared with you earlier, I can also share it right now. Now, if you take a look at the way I calculate, so here, now this is yt minus 1, right? Yt minus 1 can be party, pop, or TV, or study. There is four possible state of yt minus 1. So for yt, in order to go to yt equal party, there is four chains. One come from party, the other come from pop, right? The other come from TV, and this one come from study, right? So this is for transition from party to party, pop to party, TV to party. That's exactly what the formula say. So you take the maximum over yt minus 1, when you take the maximum over t yt minus 1, you get this number. Okay,
Yes.
so this number,
Well,
yep,
the first column you multiply with 0.25 is that uh,
this is the
uh,
prior.
yes, this is
This
the
is the,
prior. So okay.
yeah, okay. So because I don't know the probability of observing party pop or TV or study, I don't know. I have no
So we
information. So
s- so we
let
assume
assume them to,
they are equal.
yep. If you have no
Oh,
information, just assume them to be equal.
oh yes, yes, I understand.
Okay.
Okay.
Mm.
Yes. Okay.
All right. So is there any other questions? Other guys, are we clear? Okay.
Yes.
Thank you. So
Right. Yes.
that's
Thank you,
good.
James. Yes.
So
Very good.
I hope that you guys can understand this very well because it's important. If you can capture the idea behind the scenes, then we can do a lot more. All right. So back to the discussion. We have hidden Markov models and some application of that. And again, I would like to express that we don't use hidden Markov model very much nowadays, but you must know about it, and hopefully someday if you encounter some application that requires some lightweight approach, then hidden Markov model can be one of them. Okay, so in the last few minutes I will discuss about something related to support vector machine before we close the class. So let's see, do I have, here we go. Okay, where am I? All right, so
Teacher, teacher,
yep.
can you talk a little bit about the conditional random field? Because I think the time is not too much, so we can we move the spot vector machine into the later?
Okay, conditional random field.
Yes,
Okay, okay, wait a minute. Let me, because I didn't prepare that one in the material, so I better show you in some other place.
yes,
Okay,
that's no
wait a
problem.
minute.
Yes, okay, thank you.
Okay. Okay, so this is hard to find a good material for you in case of conditional random view because um, they were written in many format and in many way. So I think that if you are reading something like the Medium post, you can find some brief information about conditional random view. Basically, conditional random view trying to modeling the conditional distribution. In other words, it does not solve the John probability, but it trying to calculate the conditional probability p y given x, where y is the hidden state, the label, and x will be the data. Okay, so this formulation is something that you already know. It's not that hard to understand, but the key here is that your input data is sequential rather than just a value or a vector. Is a sequence of observation. Okay, so given that, we have to take the context of previous state into this prediction, and in order to modeling this behavior, they try to propose some sort of feature function. We call that feature function. Okay, so it's a feature that have multiple value. The feature function will receive the input vector x, of course, the positions of the data point, which is t, which position you are trying to predict, and the label of previous data point I in the -1, and the label of data point I. So basically, the feature function is something like this one. As you can see, it's a function of the data x, a sequence of vectors, okay? And I is the index which you are interested in right now. And our I-1 is the label of the previous data point, and Li is the label of the current data point. So you can think of this feature function as a way to define the label, the relationship between the label and the data. For example, if you are doing NER problems, okay, or may you call it part of speech tagging, then you may want to tag if a word is a noun, a verb, or adjective, and something like that. Then you can see that this feature function can be defined as follows. It's equal 1 if the label before the current word is a noun, then the label of the current verb is a verb. If it is right, then the feature is 1. It is a match, right? Now followed by a verb, then this feature function receive the output value 1. Otherwise, it's 0, which means you impose some sort of strong assumptions over the relationship. If you see a noun, and then next you will see a verb. Okay, so that's the role of feature function. It defines some sort of relationship between two consecutive state. Okay, and you can see here this is another feature function. It's a if you see a verb, then the one after it should be adverb. Otherwise, this feature function will fail. Okay, it returns 0 otherwise. So you may have a collection of feature function, a lot. Okay, and given that you are ready to modeling this probability, and so the probability of the label y given the input data x will equal to, well, you try, what you are trying to do now is modeling s in a conditional field. We're trying to build a conditional field. It's gonna be the exponential function. Here, EPX is exponential functions. It's going to be the E exponential function of the sum over I and the sum over J of those feature function. Well, the role of feature function, as I mentioned, is to define the relationship between two consecutive hidden state yi minus 1 and yi. Okay, so when you take the sum over I, what do you have? You have the sum over all the feature you have. Think about like feature selection in neural network. A feature probably say a neural cell, it will signal like 1 or 0. Okay, 1 is active and 0 is inactive. So each feature show you the presence of some feature in this setting. So given this sum, what you have is well, what you have here is the combination of all the feature where lambda turn out to be some sort of well, the weight. Okay, some sort of weight. So we combine those features, but some features are more important than other features. You see? So the sum over this give you an idea about how do we measure the occurrence of feature in our input sequence. So for example, I have a sequence say I go to school. Then the first one is the feature of now followed by a verb. And obviously, if you put the label now and verb on the first two words, that feature will activate and it give you the output signal 1. And lambda j will be the one you are using here, which is the combination of all the features. So again, if you have j feature, if you have j feature, then you have to sum over j functions like that one. Do you get it? So feature function is a way to extract some information from the input at time I, at step I. Okay, and you sum over all of that, then you get the value in the bracket over here. And you will divide by j zx. Zx is like the sum over everything. Then the probability of yx with lambda will be the formula you see over here. This is similar to what we have now so far, except that now for conditional random field, we don't see the probability that much, but what we see is the feature function instead, and use that one to modeling the probability of the label y given the input sequence x. Okay? And that's the key. Now, what you are interested in is you want to find the optimal y given this probability setting. So, what we do now is we try to estimate the parameters lambda, because as I mentioned earlier, you define the feature function. So you don't know which feature is important or not important. Therefore, you set up the weight lambda j for each feature, right? And because of that, we now have to estimate the lambda weight using maximum likelihood estimation. Now, to apply these techniques, you will use the negative log likelihood, and this L is the function you have to optimize. And if you take the negative log likelihood like this and apply to the formula, you can easily discard the exponential function over there, and you will waste something else. But right now, let's keep that one. Overall, if you take the derivative of the L function we mentioned earlier with respect to lambda, then you will have some formula like this one where fj is still the feature function you have, but in form of a vector instead of the single value. Okay, and so fj here is nothing but the sum over all the feature. Okay, and if you keep computing this thing, it will end up with the gradient update equation, because this one on the top is the derivative of the loss function with respect to lambda. Therefore, you can apply gradient descent to update the lambda over time using these feature functions. And then over and over, after a while, you will get all the lambda you have. And as you have the lambda, you already have a way to calculate this probability. Okay, you have a way to calculate this probability, and if you can calculate this probability, you can easily get the conditional distribution here using Bayesian rules. Uh, it will be the probability of the joint distribution divided by the probability of the data. But you don't care about the data, therefore it also be argument max of the joint probability. So in that sense, you can now get the sequence of hidden state y given the data. That's the idea of conditional random view. And well, when you take a look at the conditional random field, you will see that hidden Markov model tend to be a special version of conditional random field. It's very special because, well, look at that setting. It may be uneasy for you to recognize that, but a lot of people do the analysis on that one, and they figure out that hidden Markov model actually a private case, the special case. Okay, and there is a difference between the conditional random field versus the hidden Markov models. The hidden Markov models, by definition, we have so far is the generative models, which give you the estimation of the joint distribution. Why for CRF, what we use for CRF is for mostly classification. Okay, and what it modeling is the conditional probability distribution rather than uh, the joint distribution, of course. And one thing important that the conditional random field does not rely on the independent assumption. Okay, they say that the label are independent from each other. There's no relationship between the labels. You don't care. Well, this is good, right? Because if you have some dependency between the labels, there would be a risk. Sometimes you cannot define that behavior. Sometimes you cannot know which label depend on what label. That's just impossible. So we use conditional random field in a lot of application, and it's contrast with hidden Markov model. Why nowadays you see hidden Markov model being used in not so many application. Conditional random field actually more popular. It has been widely used for several years. Even now, in some neural network, they still use the conditional random field. So if some of you read papers nowadays about sequential modeling, you will see conditional random field in some model, especially deep learning model. For example, if you are doing ASR problems, speech recognitions, nowadays they use conditional random field as the the last layer of the neural network. In the very first few layers, they will use, let's say, they will use LSTM layer stack together, and then in the last phase, most of people will apply conditional random field, and you can find this in some document, in some paper. I can show you. Let me find one paper for you. Likewise, the network is very slow. Sorry, uh, really slow. All right. So you are seeing a repository that implement the automatic speech recognition using conditional random field. It takes you a while to read the description, of course. But this one say you can actually use conditional random field instead of CTC. You can replace it by CTC also. Um, in my experience, a lot of people who work with sequential modeling, especially for speech recognitions, they use CTC as the last layer. But some other people also use conditional random field. So there's uh, no restriction here. Some of you can prefer CRF, some of you can prefer using CTC. That's fine. Okay. Okay. Let's see if I can load the paper. All right. So you can see this is the paper written from that repository, and what you see is the here are some description about CF based modeling for the models. It's very simple. I think that in the paper they don't describe a lot about how do they derive the formula for CF objective function. That doesn't matter because like CF is something so standard that that's why they don't even care about explaining about it. But it's good to know that until nowadays people still use CF for some problems, and it's good. If you take a look at those information, like some evaluation using different approach than using CAT here, as you can see in this table, table number 3, um, the the error is actually very low and good in terms of recognition performance. So I believe you can rely on this approach, and using CF is also a good option. I'm not saying they are the best one, but still adequate. Okay. So that's about conditional random field. So hopefully some of you may interested in this one, and if you like, I recommend you read some repository about this. Maybe this one is a candidate. It was proposed back then in 2019, but still in development right now. As you can see, they still commit and update the repository. There are some paper related to this one. So if you want try it out, they still have some other update. This is the newest paper of this author. You guys can check. Well, same the same lab. So this one is also another paper, recent paper of the team about multilingual and cross-lingual speech recognitions. And I think that is a good idea. Sometimes when you speak in Vietnamese with English, and sometimes even if you are speaking with English people, sometimes you cannot pronounce the name of some food by using English, but Vietnamese like phở or bánh mì, something like that. So in that case, the mixing between language is something occur in modern world, and you have to accept the fact that we need to build multilingual and cross-lingual speech recognition system. And so this paper proposed an idea to improve that problems. And so you can see some more detail here in the paper. I suggest that this one is a good approach, even though I cannot understand this language. It's the mix between Spanish and Italian, which I don't know any of them, so sorry about it. But if you can take this approach and apply in Vietnamese and English, and you gather enough corpus, you can do well. So that's the whole idea about this one. So yeah, I think that's it for today. So uh, I'm sorry that I didn't prepare the detail about conditional random field, because I think that you guys may not so interested in that, but good to know some of you want to know. So please don't hesitate to read more paper, and if you need any advice or any discussion, you can come and contact with me. I can give you some information later. Okay, so that's it for today. Thank you guys for joining. I will see you next time. See you guys.